All right, now we're talking. Welcome back to the channel, everybody. Back in January of 2021, a paper was posted online that sent shockwaves through the scientific community. Published in the journal Physical Review, the paper claimed to have discovered evidence for the first time of the long-theorized but never before detected tortillon field. This video is brought to you by me and my sponsor, Brilliant.org. Don't worry, this isn't going to be too hard. What we do need to go there, though, is the concept of curvature. Like stress is also a tensor, but unlike stress, curvature is a little harder to visualize. Basically, curvature describes how much something is curved. You can probably guess that if I took this flat piece of paper and I scrunched it up into a ball, its curvature would increase. It's very unlikely that the torsion field even exists. One way to try and detect the torsion field is to perform an experiment where you apply a force to a material and measure how much it distorts in response. They placed the container in a strong magnetic field and applied a small oscillating magnetic field perpendicular to the main one. Maybe there was some kind of mechanical resonance going on, or maybe it was picking up some kind of electrical noise. The data was real, but it wasn't an observation of the torsion field. It was actually an observation of something called the inverse piezoelectric effect. The inverse piezoelectric effect is similar to the piezoelectric effect, which is well known in the physics community. Who knows? Maybe the torsion field is real, but we just haven't detected it yet. I'm going to link to them in the description below. Hopefully this video helped you understand them a little better. If that's true, it would obviously be here. But even if it's not, there's still a lot of interesting physics to be explored. The piezoelectric effect is what's behind the operation of things like microphones and certain types of sensors. It happens when a material changes its electric charge distribution in response to applied mechanical stress. The inverse piezoelectric effect is basically the same thing, except instead of applying mechanical stress, you apply an electric field. But after ruling out these possibilities, they realized that their experiment was producing a real physical effect. They published their results in the journal Physical Review, and the physics world was thrown into chaos. Some people thought it was an amazing discovery, maybe the first observation of the torsion field ever. Others thought it was a hoax. Was it even a real observation? Or was it just some kind of experimental error? Then they looked for a change in the signal from the NMR that might have been caused by the torsion field. Unfortunately, they didn't find anything. But then something weird happened. In the case of the 2021 experiment, the researchers were applying a strong oscillating magnetic field to their container of water. That magnetic field created an oscillating electric field inside the water molecule. The electric field caused the water molecules to distort slightly, which created a pressure wave that leaked out of the container and caused the equipment to vibrate. It's a real effect that can be explained by established physics. There's nothing pseudoscientific about it. But it's also not the torsion field. After they finished their experiment, they noticed that their equipment had started vibrating at a frequency that matched the frequency of the applied magnetic field. At first, they thought this was a fluke, but then they repeated the experiment several times and the result was always the same. Their equipment would stop vibrating whenever they performed the experiment. If the material's torsion field is strong enough, then it should exhibit some sort of response that we could measure. In 2021, researchers at the University of Göttingen in Germany attempted to do just that. They wanted to find out whether water had a torsion field. And if it did, then it might be detectable using nuclear magnetic resonance. Nuclear magnetic resonance, or NMR, is a technique used to study the structure of molecules. It relies on the fact that atomic nuclei with an unpaired spin, like hydrogen, can be made to resonate at a particular frequency when exposed to a magnetic field. But the idea has its merit. By developing a theory of the torsion field, we may be able to find a way of describing how matter responds to external forces that is more general than what we currently have. And maybe, just maybe, it could help us answer some of the outstanding questions in fluid dynamics. That's why people are still researching it. But how do you quantify that mathematically? Well, That's where these indices come in. Here, take a look at this. Imagine our flat sheet of paper as our universe and the x and y axes are spatial dimensions. If our universe is flat, then the curvature in both the x and y direction is 0. But if we curve the paper, then the curvature along the x-axis and the y-axis is no longer 0. And if we make it really curved, then the curvature is really high. Just bear with me here. In physics, we use something called tensor calculus. Now we can finally move on to the torsion field. It was developed way back in the 18th century and has stood the test of time. So why do we even need the torsion field? Well, here's the thing. Elasticity theory only applies to solid objects. If you want to describe how fluids respond to external forces, you need a different theory. And unfortunately, our current theories are pretty lacking. We have things like Navier-Stokes, which is pretty good. But there are a lot of phenomena that we'd like to understand better. Things like turbulence, for instance, are notoriously difficult to model. And I wouldn't even get started on things like chaos. The torsion field is a hypothetical field that has the same mathematical properties as curvature, except for one crucial difference. While curvature describes how space-time is curved around massive objects, the torsion field doesn't. Instead, it describes how matter responds to basically, the torsion field is a way of quantifying how much a material resists changes to its shape. You can see why this might be useful, because lots of important physical phenomena can be described this way. For instance, elasticity is a property of materials that depends on how easily the material-less shape can be distorted without breaking. Tensors are basically just ways of describing relationships between different physical quantities. A good example of a tensor is stress. Stress is a measurement of force distributed over an area. Or in other words, it's a measurement of how much force is pushing against something for every square meter of area. We can describe stress as a tensor because it takes the indices. You've got your force, which we'll call F, and then the area over which it's distributed, which we'll call A. So stress is written like this. See, that wasn't so bad. Today, we're going to be talking about the torsion field, one of the most controversial ideas in all of physics. And if you know anything about the torsion field, you probably already know it hasn't exactly been well received by the wider physics community. Most physicists would tell you that the torsion field is pseudo-scientific, mumbo-jumbo, and not worth the paper it is printed on. But there is still a vocal minority who think it could be the next big thing in physics. It was a big deal, kind of a scientific rock concert, if you will. But then just like that, it was over, and life went back to normal. The party ended, and nobody seemed to care anymore. And I feel like that is a real shame, because there is a lot more to this story than just whether or not they found what they were looking for. And I think it is important that we talk about this, because this is even the first time something like this has happened before. It won't be the last. And honestly, it's an incredible opportunity for us to learn how science really works. So here we are. So what is it? To understand what the torsion field is, we need to understand a little bit of math. Now, tensors can get way more complicated than this, but fortunately, we don't need to go there today. Okay, so we have a rough understanding of tensors and curvature. But wait a second, elasticity isn't a new idea. We already have a perfectly good theory that describes how elastic materials work. It's called elasticity theory. Now, I'm not saying the torsion field would solve any of these problems. It definitely wouldn't. Unfortunately, the trouble with the torsion field is that it's almost impossible to detect. In order to perform their experiment, the researchers used a cylindrical container full of water. At first, they thought it was a problem with their equipment. It turns out that the truth is somewhere in the middle. What happens is that the electric field causes the material to change its shape. It's a tiny effect, but it's measurable with the right equipment. I know that's probably disappointing, but it is also kind of exciting because it means that there are real physical effects that we're not yet fully aware of. If you're interested in learning more about the torsion field, there's some great resources available. As for me, I'm gonna keep on learning about the torsion field and everything else. Thanks for watching.